Hi everyone, my name is Kai and I will be talking to you guys about the one-way analysis of variance, or a one-way ANOVA. Alright, so we use this test to determine whether there are any statistically significant differences between the means of three or more independent groups. And it is called a one-way ANOVA because there is only one independent variable. The purpose of this test is to test the difference between the means of, just like I said, three or more groups. So it cannot tell you which groups are statistically different from one another, but that there is a difference among the means of the groups. So we are still testing against the null hypothesis, which says that all means are the same, or that the mean of group A, B, and C are all the same. The alternative hypothesis, which is what we hope for, is that the mean of one group P does not equal the mean of another group Q. For some groups, P does not equal Q. So we want to prove the null hypothesis false, and we want to be able to say that there is a difference in the dependent variable that is significant due to the manipulation of the independent variable. So let's discuss some requirements for running a one-way ANOVA. So we need at least one categorical independent variable, and this should have at least three levels, or three different conditions, and one quantitative dependent variable that is continuous. So here are some examples: something test score, hours of sleep, price of soda, inches of growth. So these are all things that can be compared to one another and things that can be measured, and they can range from a scale as well, just like the example I put in here. Again, so let's look at an example. In this first one, your independent variable is Instagram use, and you assign groups to a low, medium, and high levels of use to find out if there is a difference in their state body satisfaction. So their current body satisfaction in that particular moment. So the second example still uses the same dependent variable. However, we do switch up the independent variable in this example, and we assign them to a nature, fitness, and beauty photo group. So let's look at that example in a little more detail, just so you guys have a little more understanding of how it could look in a journal article. So in this study, there are 60 female participants, and they are randomly assigned into those three conditions that we just talked about. So we want to make sure that there are an even spread of participants and that they are randomly assigned. And we want to look at the dependent variable, which is body satisfaction, and this can be measured with the scale, and the scores range anywhere from 6 to 54, with higher scores indicating higher body satisfaction. So we just discussed three of these assumptions. So now let's look at these last three assumptions, which are all going to be tested in SPSS. So no significant outliers. This one you will be able to find when you run the ANOVA in SPSS, and the researcher can decide to remove that outlier if it is beneficial for the study. And then the dependent variable should be approximately normally distributed for each level of the independent variable. So this just means that we should see that bell curve for every single one of the groups. And then we also want to make sure that there's a homogeneity of variances. So this can be tested with the Levine's test in SPSS. This just means that the spread, that curve, is similar for each group, as in there's not one group that is extremely narrow and another group that is extremely wide. And so let's look at how to interpret the results. So the first thing is that test of homogeneity variance that I just talked about. So in this example, we can see that it is non-significant, and which is what we want. We want to make sure that there is no violation of the homogeneity of variances. So if that is significant, that means that it has been violated. However, it is not significant, so we can move on with the study. Now let's look at the F-test in ANOVA. So the F-test determines whether group means are equal. If the null hypothesis is true, then the F value is going to be close to 1, and then a large F value means that the variation among groups means is more than what you would expect to see by chance. So we want that large F value, and let's go into more detail about that. So what do we mean by variance between the means? So this is going to be the mean of each group compared to the overall mean of the entire study. So as you can see here, we have group 1, group 2, and group 3, and the means are all on this little map compared to the overall mean in the middle. And then this is the numerator, and the denominator is the variance within the distributions. So this is what it looks like. It's going to be how much variance is within each of the groups, or basically how each participant in the group is doing to another participant within that same group, or that internal spread. So here is another visual for the variance between groups. So we want a larger between group variance because, again, we want to see difference between the means, right? So you can see that smaller group variability, that just means that there's not too much variance from the overall mean. And we want that larger group mean. So let's move on to the denominator, or the variance within the groups. You can see on the one on the left, this is going to be a very low variance within the group. Again, that is what we are looking for. And then the one on the right is a very large variance within the group. So because we want that F statistic to be large, that would mean that there is a more significant difference. We want the bottom, the denominator, this variance to be smaller, and we can detect a greater difference that way. So if the null hypothesis is true, then the F value would be 1 or very similar to 1 or below. So a perfect 1 would look like all of the distributions are just layered on top of one another. So that would be a true null. There is no difference whatsoever. And then we reject the null hypothesis if the variance between the groups is much larger than the variance within. So this would mean that at least one of the means is an outlier, and that's what we want to see. So let's look at an actual ANOVA table. So this is going to be what it looks like once you run the test. And again, sum of squares here, let's start there. This is going to be that total variation within the groups. And then degrees of freedom, or how much they are able to vary within that. We're going to divide the sum of squares by the degrees of freedom to get that mean square, or the mean variance. And again, that would be that between groups, and the bottom would be the within group, and this would give us our F statistic. So in this example, the mean square between groups is very large. As you can see, it's 45, whereas the mean square within the groups is 10. So the difference between the group means is very large compared to the denominator, and that gives us a very big F value of 4.5. And As you can see, this is statistically significant. This shows that the p-value on that last column is going to be basically showing how likely the F value calculated from the test would have occurred if the null hypothesis of no difference among the group means were true. So in this case, there is only there's less than 5% chance that the null hypothesis is true, and there is a significant difference detected between the groups. Now let's look at an example where the null is true. So on this table, as you can see, that mean square, or the difference between the groups variance, is very small. It's 0.08, whereas the variance within the groups is 0.55. So if you can imagine, this would mean that the bell curve is just ever so slightly different for every single one of the groups, and that average from the mean, they're all very much close to that average mean, and that gives us a very small F value of 0.15. And so in this example, the p-value testing for the F value against that null hypothesis is 0.86. So we cannot conclude that there is any difference among the groups due to the independent variable. And last thing, just want to remember that a one-way ANOVA only confirms a significant difference between the groups. In order to find which groups are significantly different from one another, we must perform a post hoc analysis following this. All right. Thank you guys so much for listening, and I hope you guys have a great day, and I hope the ANOVA makes a little more sense to you guys now. Thank you.